Okay, so in this recording, we're going to go over trig substitution. And if you open up to chapter 8.4, you'll see this like big table of information. It's kind of jumbled and honestly seems confusing. I would think it would be confusing for you. But the basic idea, though, is that we're going to learn how to deal with integrals that involve square roots of differences or sums. And the way that we're going to do that is by imagining that this square root is going to be calculating one of the sides of a right triangle. That's the whole idea. And if we assume that something of this form, one of these forms is the length of one of the sides of a right triangle, then we can use trig identities to convert the integral in terms of x to an integral in terms of the angle on that right triangle. It seems kind of jumbled, but I think that this first example might illuminate it a little bit. Okay, so without even looking at the rules, okay, just look at this and okay, I see that there's no clear way that I would know to integrate that. But I do see that there's this square root of 9 minus x squared right here. So if I were to draw a right triangle, okay, and I imagine theta right there, so theta is the angle that we're going to be considering. Now, which side of this would make sense for that this radical to be on? Right, so it's this squared plus this squared is equal to that squared, right? So what we could say is like that looks like that could be the hypotenuse of the triangle, right? And one of the other sides is going to be x squared, okay? And we can just choose it to be sine. Okay. And then this side here would be square root of the hypotenuse minus that other side. Okay. So when I see the difference there, I'm assuming that that's the length, that 9 is the length of one of the sides, and that x squared is the length of one of the sides. When it's a difference, it must be the case that the 9 is the hypotenuse. I know that. Right? The x squared could go right there or right there. Doesn't matter. Your textbook seems to think that sine theta would be the one to use. So, but you could just as easily put it down here and do cosine theta, and it would look different as you're working through it, but it would also work. So, okay, why are we doing this now? Well, now that we have this, we can say, oh, I know that sine theta is equal to x squared over 9, or in other words, 9 times sine theta is equal to x squared. Okay? Opposite over hypotenuse. Okay. Well, as I mentioned at the beginning of the recording, the goal is to convert all these x's to thetas. So I see that 9 sine theta is equal to x squared. I see that this x squared is, I can replace it with 9 sine theta. Okay. Also, I see that if I'm going to try to replace this square root business, the radical business, then I see, well, maybe cosine theta is equal to this over 9, right? Or I can say that, running out of room, I can say that 9 times cosine theta is equal to this radical. So, oh, I need to be careful here. I just noticed something. That 9, if it's going to be the hypotenuse, that's the hypotenuse is squared, right? So actually, I made a few mistakes here. That should just be 3 and x. And then we have this squared plus that squared is equal to that squared. Okay. All right, so silly mistake. So now let's look at what's going on here. Sine theta, so is equal to x over 3. So I know that 3 sine theta is equal to x. And if I square that, I get my x squared. So I don't know how that worked out that way, but okay, so I can replace that. And now I need to look at the radical business. So I see that cosine theta is this over that. So 3 cosine theta is equal to that radical, 9 minus x squared. I'm going to need dx somewhere too, but we'll get there. Oh yeah, that's all I'm missing, right? I have that, and then I have x squared, so I have this and that. I just need dx now. And I can get dx from this line here. So that'll be 3 cosine theta is equal to dx. Take the derivative on both sides here. So I think I have all the things to replace each x here. So this will be the integral. So what's dx? Dx is 3 cosine theta. Oh, when I took the derivative on both sides, I should have had my d theta here. I was missing that. So dx is equal to 3 cosine theta d theta. And then x squared is 9 sine squared theta. And the radical is 3 cosine theta. Oh, that works out nice. 3 divides 3 out, cosine divides cosine out. Take out the 1/9. And this is going to be 1/9 of cosecant theta d theta. I have no idea what that integral is, but I know it's one of the basic integrals from the table. And I look to see, and this is going to be on the integration formulas, number 15. So this is negative cotangent theta. So this would be negative 1/9 of cotangent theta. Let's see. But we're not done. We need to convert back to the variable x. So I look at cotangent theta. It's that over that, right? So then it's be negative 1/9 of x over that. Oh no, sorry, not x over that. It's cotangent. It's this over that. It's 9 minus x squared over x and all plus c. Okay. And that's it. So again, trying to pay attention, at least like the way that I think, trying to pay attention to the rules that they give you here, it's not as, it seems confusing to me. And I just think of it like make a right triangle and piece it together so that the pieces that you make, you can replace all of the x's in your integral by thetas. Work through it and then go back to your triangle at the very end. And replace them back. Okay. So maybe let's do another example. Okay. All right, what was the example? 4x squared plus 1. So dx of the square root of 4x squared plus 1. Okay, so again, we just want to replace all the x's. Just ignore that table business over there. Let's just think of this as somehow being measuring the length of one of the sides of a right triangle. And it helps to rewrite this as 2x all squared plus 1. So then if I draw a right triangle, then of each of these sides here, the only one that would be the sum of the squares would be the hypotenuse. So this would be, and 1 is like 1 squared, right? So then if you make this your angle here, then you can say that this is like 2x and maybe like this is 1. And then everything works out. That squared plus that squared is equal to that squared, right? So it matches up. Now let's see if we can somehow replace all of this. So I see a dx. So because I see that I'm going to need a dx, and I see that I have x right there, the derivative of 2x is going to be dx. So if I do, I don't know, I suppose I could do that over that. So that could work, maybe. I could do, I gotta like think. Like I'm avoiding the table. I know that there's like set rules, but I think that really thinking out. So how do I get that? So cosine would be adjacent over hypotenuse. So 1 over cosine would be hypotenuse. So 1 over cosine is secant. So I know that secant theta is that over 1, right? Good. So now I can definitely replace the numerator. I just need to get my dx now, and I can do that any number of ways. I want to do maybe tangent. No, yeah, tangent. Because tangent would be that over 1, and that's the easiest way to isolate x. So like that. So then I can do the derivative of tangent. What is that? Why do I always read the derivative of tangent? Derivative of tangent is secant squared. Okay, so secant squared theta d theta is equal to 2 dx, which means that 1/2 secant squared theta d theta is equal to dx. All right, dx. And this radical, I can rewrite this in terms of theta. So dx is 1/2 secant squared theta d theta. So I'll take out that 1/2 secant squared theta d theta all over secant theta. Oh, that works out nice. And this is just secant theta d theta. I think that's negative cotangent. Where's that table? Negative, no. What is the integral of secant? Oh, yeah. I don't know how some people remember these things. So the integral of secant is natural log of secant theta plus tangent theta in absolute value. Whenever plus c. But we're not done, right? We have to convert back to x. So secant is that, tangent is that. Oh, it works out nice. So altogether, it is 1/2 natural log absolute value of that. So square root, we're going to write it all out now, 4x squared plus 1 plus tangent, so plus 2x outside, plus the integration constant. Okay, and so anytime that you see a radical, just a square root radical, you can do this type of substitution, and it's actually not as hard as some people say. It's just you draw your triangle and you take your time, and just remember your goal. Don't try to like look up the table in your book and try to follow what they have, because I think it's confusing. Just remember your goal. You want to replace all the x's by thetas. Okay. So maybe let's do one more. X squared plus 1 3/2. X squared plus 1 3/2. Okay, so integral of dx all over x squared plus 1 to the power 3/2. Okay. Now I don't see immediately a radical square root sign. It's kind of funny that that's what I was just emphasizing, but I don't see one there immediately. But there is one. Because this is like the 1/2 power being raised to the 3rd power for this quantity in the denominator. So then, acknowledging that, I can then say this is like square root of x squared plus 1 all cubed. All right, so now immediately when I see the addition, there's only one side of the triangle that's going to result from an addition, and that's the hypotenuse, right? So and I just know that this squared plus that squared is equal to that squared. So I know this for sure. Now I just got to think before I act and say what's going to be the easiest way to put an x. I can put the x there and the 1 there, or I can put the x there and the 1 there. I just have to think ahead of time. What is going to make it easiest for me to get that dx? The easiest for me, I think, would be for the tangent, right? If x is right there and 1 is right there, then tangent theta is just equal to x, and that makes life easier. And I just take the derivative, and I'm good to go. And also, it looks like secant is going to be that over 1, so I have the radical there as well. So that's pretty nice. The secant theta is that over that, so that was the easiest way for me to get the radical. secant. And then to get the dx, I see tan theta is equal to x. So I just did this one, I think, right? Secant squared theta d theta is equal to dx. It looks like I can replace everything, right? So this is going to be, what's dx? Secant squared theta d theta all over secant cubed, right? The radical is secant, so cubed. So this is going to be 1 over secant theta d theta, but that's just cosine, right? And the integral of that's sine theta plus c, always. And what's sine theta? Sine theta is x over that, right? So opposite over hypotenuse. So x over root x squared plus 1 plus c. Your textbook probably will like rationalize this. What would that look like? It's just x squared plus 1. Maybe that's how they write it in the textbook. Oh, surprisingly they didn't. Yeah, I think that's it. But yeah, so this is actually a pretty fun game. At least I think trig substitution is a little bit more fun because it's not just plug and chug. You have to like draw a picture, you have to think ahead of time, and I don't even know why I wrote this table up here. It's pointless. Just draw your triangle, look at your integral, look at your triangle, and try to match up the sides the way that it will work out in your favor to replace all the dx's by all the x's and dx's by thetas and d thetas. Okay. So that'll be it for trig substitution. Oh, for homework in this section, actually, because I didn't put down any homework in the last video, so so 8.3, 3 through 29, and 8.4. One through 29. That's the suggested homework for this. Okay. That'll be it.